Hello, my name is Rucha Wani, and I will be discussing my undergraduate research on organomineral associations in permafrost deposits conducted with the Delaware Environmental Institute. Projected increases in polar temperatures threaten the stability of terrestrial carbon sinks, which promotes the mobilization of carbon to the atmosphere in the form of carbon dioxide and methane. Aged carbon, which is stored in deep deposits, represents a substantial component of permafrost carbon currently stabilized below thermodynamic and metabolic thresholds, simply meaning that it's frozen. But the mechanisms governing the fate of deep permafrost carbon under changing climate conditions remain largely unknown. Mineral associations, one of the most important carbon stabilization mechanisms in soils, could contribute to the stability within deep permafrost. Our previous work suggests that old permafrost deposits contain iron-carbon complexes, which under thawing conditions release carbon compounds with incredibly unique molecular signatures. The structure of such complexes that usually play a protective role against biodegradation of carbon can change when the chemical and physical properties of the surrounding environment are altered, such as increased heat or exposure to oxygen, which could impact their ability to stabilize that carbon. Using a suite of high-resolution analytical techniques, we characterized such organomineral associations across a chronosequence of Yedoma permafrost from Fox, Alaska. Yedoma permafrost is deep, carbon-rich permafrost found all across polar latitudes. These samples were taken from a permafrost tunnel with carbon deposits dating back to 36,000 years. Our goal was to figure out if carbon and iron transport pathways differ under oxic and anoxic thawing, and how the stability of iron-3 carbon complexes changes under varying oxidation conditions while thawing. We were able to make some interesting discoveries by running a 20-day permafrost thawing incubation under separate oxic and anoxic conditions, coupled with iron extraction assays and molecular fractionation analysis of the samples. Using a TOC analyzer and a CHNS analyzer to quantify the amount of carbon in our different solid and aqueous phases of sample, we discovered that the oxic system showed a strong decline of dissolved organic carbon, DOC, in both the solid phase and thawed meltwater, suggesting abundant microbial respiration. However, in the anoxic system, the dissolved organic carbon unexpectedly increased over time in the meltwater, while the dissolved organic carbon in the solid phase decreased, suggesting a release of carbon from the solid phase to either the gas or meltwater phases. We used a modified ferrozene assay on the samples to determine the amount of extractable iron too. When looking at the iron signatures in these samples, we discovered that extractable iron 2 had decreased from the oxic system's meltwater over time, suggesting potential oxidation to iron 3. However, extractable iron 2 increased over time in the anoxic system, suggesting reduction of the iron 3 species to iron 2 species. When we look at the combined iron-carbon dynamics, we see contrasting kinetics relationships within the oxic and anoxic systems. In the oxic system, iron-3 carbon complexes do not seem to be mobilized. Instead, there is significant degradation of unstable carbon, likely by microbial activity. In the anoxic system, the dissolution of iron-3 carbon complexes correlates strongly with an increase in dissolved organic carbon in the meltwater, which is not consumed. This is supported by the substantial increase of protein-like compounds in the molecular signatures of the anoxic thaw samples over time, which was observed when we ran our samples through an FT-ICRMS to produce molecular composition plots of our samples. Whereas the oxic samples have a distinct lack of aliphatic and carbohydrate-like compounds over time. The incubation experiment has revealed that permafrost thawing under oxic conditions is highly likely to undergo significant biodegradation and mobilization of unstable carbon, likely contributing to increasing concentrations of atmospheric CO2, while deeper permafrost thawing under anoxic conditions results in mobilization of carbon out of the iron-3 carbon complexes in the solid phase to dissolved organic carbon in the aqueous meltwater, with limited production of carbon dioxide and methane. Future work will probe sequential redox oscillations to stimulate the effect of these different processes in situ. In conclusion, our work shows that the oxidation conditions of permafrost thaw can have significant impacts on the mobilization of carbon and global climate change. Thank you.